Our next speaker is so famous they wrote a song about him. You might have heard of it, you know. Dr. Jones, Jones calling, Dr. Jones. Yep, that's why I'm a speaker and not a singer. But you get given a speaker's bio and you think, oh, that looks interesting. So with Chris, I'm not going to do that because, A, I've known him for a few years, and today I discovered he's been the Vice President, the Branch Chairman and the National Secretary, with a typo, of the Australian Electric Vehicle Association for 9 years. He studied at the University of New England and he's got a BSc in Organic Chemistry, the University of Western Australia, graduate diploma. And then the interesting stuff started. PhD in Plant Biochemistry, Project Manager for E-Station, Research Chemist, the Australian co-founder of Voltron Motorcycles, and then now with Cape Brevard Technologies. But he also worked on the vertical lift, yeah? I can't wait. It's in your profile, mate. I know you've done too many things when you can't remember. Please welcome Christopher Jones, or Dr. Jones, Professor Jones. You going to be right with this, or do you want the handheld?
Jump onto my talk. I'll jump down there if I can.
Yeah. I'm sure I saw the vertical lifting on there today.
Oh, the flying machine.
Yeah, the flying machine. Have you got that in commercial production yet?
No.
Come on, hurry up.
Thanks. That's up and ready to go? Oh, good. Okay. Thanks for that. So, yeah, in my job at Cape Brevard Technologies, my official title is battery engineer, but I'm not an engineer. I'm a chemist and a plant genetics guy. But I've built a few batteries in my time, and since taking on this role, I've learnt an awful lot about batteries, how they work, the chemistry behind them. And so for this talk, that we often get asked, yeah, but are electric cars really good for the environment? And there's a lot of interesting science that goes behind determining how good something is for the environment. And so I say, define better. Some of you may have seen this cartoon before, I don't know, but basically someone's complaining that, you know, people aren't being paid enough for manufacturing iPhones, and they post this on social media, and some troll pokes up and says, yeah, well, you did that on an iPhone, you know. And I think the one down here is really quite pertinent. You know, this peasant saying we should really improve society. And he's like, well, but yet you're participating in society. How curious. And basically, in order to make the place better, you need to be part of the society that you want to make better. You know, the best analogy I've heard was the person who invented the internal combustion engine probably rode to work on a horse. The person who developed the light bulb probably worked by candlelight. You know, you work with what you've got until you come up with something better. So, just make sure I've got that right. Basically, modern life is bad for the environment. If you start doing carbon footprints and life cycle analyses of just about everything we do in modern life, it all starts to get quite depressing. Yet we're living longer and eating better food and living better lives than ever before. So something's working out. But basically everything we do, including what we currently do, takes energy and resources and generates emissions. Water, land, emissions, labour, all of that stuff is what provides the life that we enjoy, certainly here in the wealthy Western world. So nothing is free. And what was quite interesting is when Greta Thunberg said, you know, we really need to do something about emissions, and not flying is a good start, everyone said, well, how are you going to go and get your message out? You're going to go full Al Gore and you know, fly everywhere. And she says, no, I'm going to sail across. And some troll said, yeah, well, what's the carbon footprint of that sailboat? I mean, they clearly didn't actually care what the carbon footprint of the sailboat was. They're just trolls. When it comes to EVs, what goes into an EV? Pretty much the same stuff that goes into an internal combustion engine vehicle. A little bit more copper, a little bit more rare earth metals that go into the magnets of the rotor. But by and large, it's a whole bunch of metal and glass and rubber and petrochemicals. It's all pretty much the same, except, of course, the lithium-ion battery. And it is the lithium-ion battery that has the greatest emissions and energy input in the manufacture of an EV. So we'll say it up front, the manufacturer of an EV typically has 50% more emissions associated with its manufacture than that of an internal combustion engine vehicle. And almost all of that is from the battery. Now, the good news is that once it's made, in operation, it uses a fraction of the emissions, and it takes, depending on how far you drive, a few years to break even. But let's not shy away from the fact that a whole bunch of emissions are generated in the manufacture of an EV and its battery. Why is that? Well, the metals that go into a lithium-ion battery, obviously lithium is a popular talking point, but it's actually really a relatively minor component of the lithium-ion battery. It's things like nickel, manganese, cobalt, and iron that make up a large chunk of the battery's energy budget. And these are just some of the chemical processes from the ores that are dug up, smelting, sulfuric acid leaching, precipitation to make these hydroxides. And this step here, the calcining, it sounds like it involves calcium, but it's a general process that basically involves heating this stuff up to about 900 or 1,000 degrees and oxidizing the metals to form the lithium, nickel, manganese, cobalt oxide cathode material. And then that all goes into this very complicated process of eventually spitting out lithium-ion cells that go into battery pack construction. But that calcining step is a very energy-intensive step. Now, nickel and cobalt are not low-impact metals. I've shown a few mines here. The Forestiana nickel mine, that's out near the edge of the Nullarbor. The Thompson refinery there in Canada produces large amounts of nickel briquettes. That's a map of New Caledonia. From space, you can see these brown spots. If you zoom in on it, they're nickel mines. One of the largest lateritic nickel mines in the world. Now, you can't tell me that's not having some substantial impact on the island. We all like EVs, we all like our nickel. Not all of it is going into batteries, but most of it. So it's not impact-free. Emissions of smelting. Now, if you want to know where there's a nickel smelter, jump on this website, earth.nullschool.net, and you can zoom in anywhere on the globe, and you can get a satellite readout of the sulfur dioxide emissions in specific places. And in this case here, I've zoomed in on the Kolwezi copper nickel cobalt mine in the DR Congo, and that's where they mine almost all of the world's cobalt. Several miners have big operations there. And so in smelting it, it generates lots of sulfur dioxide, which can contribute to acid rain. A lot of that sulfur dioxide is recaptured and turned into sulfuric acid, which is a good thing. But basically, jump on that map and spin around the globe, and you can look for all of these big spots of sulfur dioxide. You can find a big patch over Kalgoorlie, a big patch over Ravensthorpe, big patch over Mount Isa, Olympic Dam. So you can see this stuff from space. It's an amazing website, by the way. You can do carbon dioxide, carbon monoxide, so you can work out where all the bushfires are. Very interesting. And by comparison, lithium is actually quite a benign material to dig up, and Australia is well blessed with heaps of the stuff. This image here is the Greenbushes mine. That's where something like about 40% of the world's lithium comes from, just that mine south of Perth. Very, very well-run operation, very low impact. So they dig up spodumene. Now they've just started to build, I think they've almost finished, Tianqi have finished building a lithium hydroxide plant where they finally, in this country, value-adding an ore and turning it into something useful rather than just exporting the material. And some of you may have seen this meme before, tell me more about how clean your electric car is. Well, that's actually a copper mine. It's got nothing to do with lithium. It happens to be the world's biggest copper mine in Chile. And no, that's not an oil sands site. It's looks like a fracking well As I said there, that forest probably doesn't exist anymore. Fracking is pretty destructive. Again, you can see all of the gas wells of the Darling Downs. Jump on Google Earth, zoom over Roma, and you can see the Jurakai forest is absolutely peppered with gas wells. We're having an impact on the planet, people. But as I said earlier, the bulk of the energy that's embedded in a lithium-ion battery comes from the calcining step. And this research here by Notta et al., it basically worked out that easily half of the energy in the entire process goes from turning those oxides and carbonates into cathode material. And that's largely electricity that's doing that. They need heat, and they need lots of heat. The good thing is that electricity can come from a renewable source. This is a very interesting paper. By the way, all of these talks will be available from our website eventually. We'll get there. And you can look up some of these papers. Basically, it takes 180 kilowatt hours of energy and 200 kilograms of carbon dioxide emissions equivalent, so that includes sulfur dioxide emissions as well, to make 1 kilowatt hour of lithium-ion battery. Now that sounds bad, but that 1 kilowatt hour battery will probably be cycled 3,000 times in its life, and it will be able to store and discharge copious amounts of renewable energy in its life. So it's a bit like saying that, a 5-cent coin costs 7 cents to manufacture, but it'll be used in thousands and thousands of transactions for the rest of its days. Again, nothing's free. Nothing is free, but we can do better. This is really quite interesting. It shows that different chemistries have different energy and emissions intensities. So several different studies have found that basically nickel, manganese, cobalt oxide chemistry has the most energy and emissions associated with it. Iron phosphate, wow, it's actually quite an energy inefficient process to make. Lithium manganese oxide, I believe the first Nissan Leaf cells were a manganese oxide cell, actually quite low. So the amount of energy required to refine manganese is quite low compared to cobalt and nickel. Now, when it comes to emissions in operation, I'll go back to the first chart that we saw. Basically, we know that even on a coal-fired grid, an EV will generate less emissions of CO2 per kilometre travelled than a petrol or a diesel vehicle. Now, partly that's because Australia's average fuel economy is terrible. It's about 10 litres per 100 Ks. But our electricity grid, the NEM average, is about 8 kilograms of carbon dioxide per kilowatt hour. So that works out to be about 143 grams of CO2 per kilometre. Now, compared to the average of about 200 to 250 grams of CO2 for the typical Australian passenger vehicle. So the great news is that electric cars can run on anything as long as it's turned into electricity first. So renewable energy will basically clean that up in no time. Now, we always say, oh yeah, but let's hold EVs to this really high exact standard. Well, let's scrutinise it. Well, why don't we hold our current technology to those same standards, and we'll realise that they fail pretty badly. This was a really interesting paper looking at the oil sands industry in Canada and how much CO2 is generated in the refining of oil sand petroleum products. Typical conventional oil, so Saudi Arabian sweet crude, if you were just considering the emissions of the vehicle, it's up around about 200 grams of CO2 per kilometre travelled. Factor in the amount of energy and oil required to make that litre of petrol, you're adding sort of another 10% to that. Oil sands, you're up around 350 grams of CO2 per kilometre travelled. That stuff is really, really bad. Like, it's really, really nasty. So 1 litre of petrol contains the equivalent of 10 kilowatt hours of energy, and our ICE technology throws 80% of that away out the exhaust pipe as heat and noxious gases. Petrol represents about a half of all of the crude oil refined, and diesel's about 26%, aviation fuel is about 11%. And 1/3 of all of the ships on the sea, and there are 56,000 ships on the sea right now, are moving oil products. So that's a hell of a lot. I mean, it sort of also highlights the scale of the problem that we've got to address. I didn't point it out, but I'll just quickly skip back to that picture of the sulfur dioxide emissions. You see this line here? That's a shipping lane. Ships burn the most disgusting bunker oil, which is so rich in sulfur that you can see the sulfur dioxide plumes from space. And it's not even that they're particularly rich in sulfur, there's just so many ships on the sea. And as I said, most of them are moving oil products. And once it's burned, it's gone. Well, it might take another million years to be turned into coal or oil, but at least with the battery, you can generate energy, put it in the battery, and take it back out again, hopefully several thousand times. So, in conclusion, battery electric vehicles generate 50% more emissions at manufacture than an internal combustion engine, but we know that that's pretty soon negated once it's in operation, even on a coal-fired grid, even better if you're doing it from renewable energy. Cathode production is easily 50% of all of the energy and emissions associated with lithium-ion battery manufacture. The good news is that electricity production can be renewable, and most of that energy will be consumed in the form of electricity. So we've got we've got a chance to clean that up. Battery materials can be recycled. They absolutely can be recycled, but it's still a very energy-intensive process, and you might end up using probably another 50% more energy to recycle them. But the resources don't have to come from the ground that time. So it's perhaps a bit like recycling glass. Yes, it's recyclable, but the amount of energy required to make it is hard to justify when the new stuff is far cheaper. I think we may find a point in the next possibly 10 years where recycled batteries end up being a very valuable source of cobalt and nickel and manganese materials for battery making. And I'll wrap up that, petrol and diesel are extremely energy dense. There's no doubting that. That's what's got us here today. Energy is basically proportional to affluence. But look, it comes at a cost. And the extracting, transporting and refining of oil, let alone the wars you've got to sustain to hold on to the stuff, they're emissions intense. So really, look, most sustainable thing to do is walk or ride a bike, but that's not always practical. So we'll do the next best thing. I would argue that we need fewer cars on the road, but they might as well all be electric. So thanks for your time.
Can't argue with a scientist that knows his stuff.